Recording in progress.
How we can gain an understanding of these macroscopic functions in terms of their microscopic solutions to Schrödinger's equations. Again, I said Schrödinger equations because they're different equations depending on what your Hamiltonian in the Schrödinger equation represents. For instance, it can represent electrons. It can represent translational movements of entire molecules. Okay, that is then defined by the Hamiltonian and the equation. Today, I'd like to move to our next subtopic, which is work and heat. These two words represent the principal domain where thermodynamics was developed, namely to understand heat engines. So machines that transform heat into work. And the prime example is, of course, the steam engine, which was the dominant engine for centuries. We would like to begin with the first law, namely that du equals delta Q plus delta W. I told you before that thanks to statistical mechanics, we can derive the second law, but the first law is not derived, and it's very fundamental. It has many different ways how it is being phrased, but also classical mechanics can be traced back to this first law. So if you dislike Newton, the Lagrangian equations can be derived from the Hamiltonian principle, which is akin to this law. And then given this law, you can then rederive Newton's equations. So in some sense, this is something statistical mechanics cannot derive. But this is a given, and Q is our change in energy. And these are changes in heat, Q, and work, W. And we make use of this funny delta symbol because these are not state functions, but path-dependent functions. Also process dependent. So if that was not the case, we could not extract work from an engine, right? Because an engine is a cyclic mechanism. And if you cannot extract something from it, then it's not a useful engine. Now, the iconic diagram we do for this is that we look at pressure as a function of volume, and you have some initial pressure and some initial volume. And this pressure now is very high in the beginning because you burned something, or you brought, let's say, water, you boiled it, right? And then upon reaching the boiling point, it expands 1,000 times to become a gas. And that's the kind of pressure you'd like to harvest, right? So very high pressure. We don't specify how you got it, but it's quite straightforward to imagine with a steam engine or combustion engine. So we have a high pressure. And then what happens is, of course, your chamber or your combustion chamber or your engine chamber will expand and do the work, right? Physical work. So it expands until it reaches some final pressure and final volume. Now that's the end of its expansion, right? And now it contracts again to close the cycle. Of course, the pressure is low here, and we are moving back. And that's when we enter the next cycle of combustion or steam generation or whatever. So that's the cycle. And now we have two integrals we can consider. One for the returning path. Let me indicate a little arrow just so that it's easier for you to remember. And then also the integral for the expansion. Let me draw this with vertical lines. Now, this integral, let's call it work expansion, is the integral over your volume change and of the expanding pressure curve. You go from initial to final. That's a lot of work you get, but then to return to the initial state, I need to compress again, and I will have to pay a little bit of work for doing that as well. Now that would be the opposing direction. So you'd have a sign change. I can flip that sign change. Sorry, compression. And the work you can extract is the difference between these two, right? Now, if you can calculate that, then you know how far you can travel for a given curve, right? So for a given engine, and for a given fuel that will generate a certain pressure. Now, this is purely the work view on things, right? So your delta W is the expansion, right? And so the running variable here, the crucial variable here is the volume, right? So we integrate over the volume change, right? So in other words, my delta W is a dP, dV times the pressure. Right? Now, for the heat, I think it's clear. The crucial property is the temperature. Right? So heat has got to do with temperature and work with volume. Far so good. So this shouldn't be new to you, maybe a refresher. But let's now try to make use of our newly developed understanding in terms of Boltzmann probabilities and partition functions. So let's look at du, and we can now insert our statistical mechanical average. You recall that this is the weighted probability sum over my energy states. And I now have to consider the total differential of a product of two functions, right? My Boltzmann probability and my energy. Right? So if I differentiate a product, I should apply the product rule. And that means I have two terms here. One with the differential of the energy and one with the differential of the probability. And I have selected to place the differential at the end. Right? This is a convention that is commonly made, because if I wanted to integrate, I would come with the integral from the left, right? And then I would have the integrand sandwiched between my differential and the integral symbol. And in some sense, you have a sort of you have that already written here. The summation symbol is nothing else than a discretized integration symbol, right? Now that discretization might be very coarse and not a good idea to approximate it by an integral, but math-wise, an integral is nothing else than a summation over many terms, right? Arbitrarily many, but now let's look at this first term, right? And in particular, the differential of the energy. And this energy, so if you remember, our du should be consisting of two terms, and the question is now, which of these terms is the heat-related one and which one is the volume-related one, right? Now, the energy of my Schrödinger equation, there's no temperature in it, right? So for that reason, let's go by saying that's the volume-dependent term. And my dEj, I can expand by virtue of a differential where I say this is my derivative with respect to volume times dV. Now I basically changed my variable, right? And I can, you need to remember, I can write something like this. right? And so from that, by multiplying with dV, I get that expression, right? Now, if you look closely at this sum here, you will notice that my dV is independent of my state. So I can pull it in front. And this term here is precisely the term we used yesterday to calculate pressure on Tuesday. Right? So this first term here is simply minus P dV. And that's, as you recall from here above, simply our change in the work. Right? Any questions so far? Is the derivation clear? Yes, please.
What does it mean to have a partial differential followed by a differential? Like sigma v dv. Does that mean you have to differentiate twice?
No, the differential is not a derivative. It simply means you're going to slightly vary something. In this case, the volume. Right? And you multiply the small variation in volume with the derivative of the energy with respect to V. Right? And that derivative is just the slope of the energy with V. And this slope is pressure, right? That's the observable we just plotted above. So the meaning of it is exactly the last equation, right? It's pressure times a small change in volume, right? So small change in work is always a small change in volume scaled by the pressure at which you're doing this. Right? Does that make sense? I hope it does. Now, you should have seen this in previous semesters in your thermodynamics, that the total differential is the differential, the change in one variable, and now or one function, and now you have to ask, what are the possible variables that could induce such a change, right? So one variable could be volume, another one could be temperature, another one could be pressure, right? So we can then write this as an expansion in all these individual terms, right? So basically, if you have the differential of a function which depends on many variables, x0, x1, x2, and so on, you can write this in terms of the sum over all these variables, where you derive your function with respect to the variable, and you multiply with the change in the variable. So this is your total differential, and these are your partial differentials, right? Those that are only evaluated with respect to a single variable. All right, so we identified the first term as a work term, and now we'd like to find out if the second term indeed is a heat-related term. So let's look at the sum of our states, and now the differential of our beloved Boltzmann probability. And now we do again the same trick. And heat has to do with temperature. So let's take the temperature derivative. And in your Boltzmann factor, you do have the temperature, the inverse temperature in the Boltzmann factor, right? So that derivative is not zero. Again, our delta T here is independent of your state. So we pull it in front of the summation. So we are differentiating Pj, but Pj clearly is a function of the temperature, but Ej, the energy, is not. So for this derivative, Ej is just like a prefactor. So I can also write it like this. So now I'm differentiating everything to the right, but since Ej is not a function of the temperature, I don't need to apply the product rule. Now you see that the derivative, the variable with respect to which I'm differentiating is independent of J as well. So I can pull it in front of the sum. Okay. So I'm to differentiate this entire sum, but this entire sum we already know. This is my expectation value of A, of E. Right? It's just the energy. And if I differentiate my internal energy with respect to T, I'm asking for the slope, right, for the change of energy as I'm changing T. And that is known as my heat capacity at a constant volume, right? The volume dependency was in the work term. Now we are, second term is at constant volume, right? In other words, the whole thing here is simply dt times Cv. And I have just shown that du, when using my expectation value of the energy, right, that indeed I recover the expression which you would encounter from classical thermodynamics. And now, again, another example of the total differential. We know pressure and heat capacity to correspond to these derivatives, right? So we have basically revisited work and heat in the first law of thermodynamics and checked its consistency in terms of the statistical mechanics and classical thermodynamics. Any questions regarding the heat capacity term and this derivation? Doesn't seem to be the case. Then I'd like to proceed to case B, which is about isocoric processes. The isocoric process is the process where you would have a constant volume, right? If I have a constant temperature for my work here, I consider something like an isotherm. I will be a constant temperature, then there's no heat term, right? And I get all the work out of the process. Now, if I have an isocoric process, which typically requires use of a bomb calorimeter. I don't know if you've seen these bomb calorimeters. These are thick steel walls, right? It's very heavy for a little volume, just to make sure that the volume is fixed, no matter how large the pressure. Right? So isocoric processes occur rarely in daily life, and they require you to invest heavily in having such a bomb calorimeter. Now, what happens here is, for such a process, we can now write a change in the energy as a change in heat plus change in work. And this would be an integral from some initial temperature to some final temperature, dt Cv minus the change in volume times the pressure. And now you have Ti to Tf. Now, isocoric means that the delta V is 0. And hence the entire integral is 0. There's no work that is done. But this, of course, does not imply that the pressure is 0. On the contrary, the pressure fluctuates wildly, which is why you need strong steel walls to withstand the pressure. In our phase diagram of pressure versus volume, you can think of two isothermals and a fixed volume where you have some final temperature and some initial temperature, and your process is getting you from here to here. Okay. So no work is being done. All you have to do is heat this thing up from one temperature to the next, right? The corresponding change in the energy is then the integral over the heat capacity of your material. Now, if you do this, if the work is zero, then your internal energy, which is a state function, is the same as the change in heat, which means your internal heat has become a state function. Now, any questions on this? Now we can consider Kc, which would be the isobaric process. And an isobaric process is if you plot the PT phase diagram, where you would have your usual phase diagram with aggregation states, with the triple point and the critical point, so solid, liquid, gas. Such a process is the one you would experience at ambient conditions if you change the temperature, let's say, keeping the pressure fixed, right? So at fixed altitude, your pressure is more or less the same, no matter how much you heat. And so in this case, your delta U is your delta Q, but now at fixed pressure, not volume, plus a delta W, right? Your work term. Now, isobaric means pressure is constant, right? So that means my delta QP minus integral over dV times P, but my pressure is constant. So it's a PC, and that means I can pull it in front of the integral. And the integral over dV is simply delta V. So in this case, I just have delta QP minus delta V times PC. Now, if I then measure my the heat, I can see that this is delta U plus delta V times PC. And this is my integral over the temperature change of the pressure dependent heat capacity, temperature dependent heat capacity, which if you assume that the heat capacity is temperature independent, would be Cp times delta T, which is known as internal heats or enthalpy. So the enthalpy you measure at ambient pressure, right? The most common form of heat we can measure. So this is only true if Cp is not a function of the temperature. So you've seen now in the beginning how within statistical mechanics, these concepts are consistently explained or consistent is concepts from thermodynamics. And in particular, they can be applied within these three kinds of scenarios: the isothermal, the isocoric, and the isobaric processes. Are there any questions on this? Yes, please.
PC stands for?
That's the pressure that is constant, right? So during the process, this arrow here denotes the process. You see it's a horizontal arrow, so the pressure does not change as you're heating up whatever you're heating up, right? There's another question, please.
Yeah, I didn't touch why changing work was negative for the isobaric process, but not for the iso.
So that's a convention, right? In which if you change the direction of your process, it goes the other way around. So don't worry too much about that. Any other questions? Okay, that's all I prepared for today. So I'd like to thank you for your attention, and I see you next week.